All right, our next topic here in equilibrium is going to be interpreting meaning from the magnitude of the equilibrium constant. Based on how large or small the number is, we can actually get quite a bit of information in terms of where the equilibrium lies, as we say it. So if we have a very large equilibrium constant, so if I can go down here and I'll draw a very large K, what that means then is that at the time of equilibrium, the products, the concentration of the products specifically, are much more prevalent than the concentration of the reactants. And what that will mean is that we tend to have a very large K. By very large, literally anything that is 1 or larger. Now, a terminology that we associate with that, if I can draw a general chemical reaction up here and an equilibrium arrow, if the K is large, and again, products are more numerous at the time of equilibrium than the reactants, we will say that that equilibrium lies to the right with the products. Now, the exact opposite is true should our K be very small. In this case, what we have is a very small number of products and a very large number of reactants, and this will lead to a very small K. If that is the case, where we have a larger number of reactants, and again I'm talking about concentration there, than products at equilibrium, we say that this equilibrium lies to the left. If we look at some examples here on the next page, first of all, we get an equation with nitrous oxide oxygen forming nitrogen dioxide. The equilibrium constant for this expression is huge, and this will tell us that there are many more products at equilibrium. We will say that the forward reaction is favored and that the equilibrium lays to the right or lies to the right. On the other hand, we could get a very small equilibrium concentration, or constant, I'm sorry, and in this case we see this small equilibrium constant, and this tells us that the equilibrium in this case lies very strongly to the left. In fact, this reaction, it would probably be difficult to even notice anything happening at all. Okay, next up is our reaction quotient, and a lot of times people have some trouble with the reaction quotient. So what I want to say here is the reaction quotient is the exact same thing as the equilibrium constant expression. So you're literally going to write products over reactants raised to the power of coefficients. So it's exactly the same as the law of mass action. The formula is exactly the same. However, what it means, and the big difference is, if you say K, you're telling me that you know we are at equilibrium. If we at all are not sure that equilibrium is occurring, we have got to use a Q. So a Q is if not sure or positive that we are not. So in order to use K, there's really only one situation where we can use K, and that is if we are absolutely 100% positive that the reaction is at equilibrium. However, if we are not sure whether or not we are at equilibrium, or we're positive that we're not at equilibrium, we have to use what's called the reaction quotient. Now, what this is going to allow us to do is it's going to allow us to predict or determine if the reaction is at equilibrium. So a few different things can happen here. First of all, when you calculate this, and again, you're going to get experimental values. When you calculate this, if the Q happens to be the exact same thing as the equilibrium constant, so the problem provides you with the known equilibrium constant at that temperature, when you run your numbers, if your Q ends up being identical to K, that is your verification that you are in fact at equilibrium. This is actually very rare to be using a reaction quotient expression and get that, but it's not out of the question. What's much more common, however, is either having Q greater than K or Q less than K. So first of all, if we take a look at K ends up being less than Q, what that tells us is at that time in the reaction, if K is less than Q, or Q is greater than K, that means that we've got too many products. and we have to get rid of some of those products by increasing the rate of the reverse reaction. And what that will do is that'll get us to a point where the products actually decreases, and we get back to a point where we are at equilibrium. So if K is smaller than Q, and actually I should probably be talking about this from the perspective of Q. If Q ends up being greater than K, that means our denominator is too large, and in order to make that smaller, we've got to get rid of some products by reforming some reactants. If, on the other hand, Q is smaller than K, what that means then is that our denominator is too large, meaning we have too many reactants. And in order to fix that, we have to ramp up the forward reaction rate so that we make more products. Now, I act like the humans can control that. These reactions actually control that themselves.